So you have been given with some resistance values and power supply voltage value and the Q point coordinates, right? So basically, this is your Q point. And remember one thing, beta is unknown here. Beta is unknown here. So the caution would be from my side, don't assume random beta value. All right, because coordinates of Q point is given, hence you do not require a beta value. All right, so let's get into the solution. Okay, so we know that ICQ, okay, which is nothing but the collector current, is equal to 2 milliampere, right? This is given. Now on the output circuit, the collector current and emitter current are, very close to each other. Okay, you could say that IC is approximately equal to IE. Okay, and therefore you can go for emitter to ground voltage equation, that is VE is equal to IE into RE. All right, or approximately you can write IC into RE. That implies your emitter resistance RE, rather RE is given, right? I'm so sorry. Or your emitter resistance, emitter to ground voltage VE is equal to 2 milli into 1.2 kilo. Okay, so kilo and milli gets cancelled, so you will be left with emitter to ground voltage VE, which is equal to 2.4 volts. Okay, 2.4 volts. Okay, let us put it in a box, this particular result. Okay, next up we have the output equation. So apply KVL to output loop. Okay, so when we apply KVL to output loop in case of voltage divider bias, we get VCC minus IC times, okay, you can write RC, or rather what I will do, yeah, ICRC minus VCE minus IARE is equal to 0. Let me write. Okay, now this IE into RE is VE, right? We have already found what is the value of VE. So that will help us in finding out this unknown resistance value RC. You see how VCC is given as 18. Let's substitute. So VCC is 18 minus IC, 2 milli into RC, which is unknown. Okay, minus VCE. So VCE is given as 10 volts, right? In the problem specification, VCE value is given. So that's 10 volts minus IE into RE, which we have taken it as 2.4 volts using the above formula. So that is equal to 0, or RC is equal to difference in potential divided by current, right? So RC is equal to 18 minus 10 minus 2.4 divided by 2 milli. Okay, so in terms of kilo, you are going to get it. So RC, how much you will get? The value, if someone can calculate, 18 minus 10 minus 2.4.
2.8 kilo ohm
divided by 2. 2.8 kilo ohm, right? So that's your RC, 2.8 kilo ohm. So you can go to your, the main circuit, and you can just strike off RC, which you have already found. All right, fine. Now let's find out R1. R1, right? Yeah, R1. Now how will you find R1? To find R1, we need to go to the input loop. Correct? We need to go to the input loop. So to find R1, you can use this particular expression, right? I mean, the circuit, equivalent circuit you can use. In the previous class, I think I have discussed about this. let's reconstruct the input network. Okay, this is your base terminal and this is your ground terminal. Okay, so base to ground voltage is nothing but VB, correct? Base to ground voltage is VB, and this is VC, this is R1, and this is R2. Okay, so using potential divider rule, okay, VB is equal to main voltage into resistance across which VB is measured divided by sum of resistances. Okay, the same formula holds good for VTH as well. Okay, so that's your VB. Okay, also VB base to ground voltage is nothing but VBE plus VE, emitter to ground, or VB is equal to VBE is 0.7 for a silicon transistor plus VE is 2.4, which we have already found in the previous step. Okay, let me just roll up. Yeah, here VE. Okay, so that will give you the VB value. So how much is it? 3.1 volts. Okay, 3.11. So you can basically substitute this VB result into your previous expression. So on LHS you have 3.1, and on RHS you have VCC, which is 18 into R2. Yes, it is given 18 kilo ohm divided by R1 plus R2. So it is R1 plus 18 kilo. Okay, so simplify this particular expression and tell me what you get it. So when you cross multiply, you would get 3.1 into R1 plus 3.1 into 18. That's 55.8K. Okay. Okay, and okay, you can, and this is 18 into 18, that's 18 square, 324 kilo. Okay, or you can further simplify. So basically R1 going to be 324K minus 55.8K divided by 3.1. How much you'll get? Did anyone calculate?
5.8.
86.5 kilo.
Okay, let me just check. It is 86.52, right? 86.516.
Yes, sir.
Okay, 86.516 kilo ohm I have got it. Okay, just check. No problems. You get any different answers, it's okay. Okay, you can cross check on this. So that's all. Yeah. So R1 also we have found. So that completes the problem. Okay. So the problem statement: design voltage divider bias circuit for the following set of specifications. Okay, for the following set of specification, design a voltage divider bias circuit. VCC is 10 volts, IC is 2 milliampere, okay, and beta is 100. VC is 5 volts. VC is 5 volts. Okay, that's all. That's all is given. So you don't know what is R1, what is R2, RC, RA. Nothing is given. Only four particulars have been given: VCC, IC, beta, and VC. Okay, so let's see how exactly we solve this. Okay, in the previous problem, at least two resistance values were given. Okay, but here nothing is being given. So this makes you could say that a concrete design problem. All right, fine. Okay, fine. Now, when there are multiple unknowns, okay, you cannot simply assume let R1 is so much, R2 is so much. Okay, because you do not know. Random resistance values may not fix your Q point at the center of the load line. Okay. Now, in order to solve this particular problem, what you have to do is somehow, you have to use the Q point specs, these two. somehow you have to use the Q point specs while designing the resistance. Okay, because if you use these Q point specs, then only you are then only you will be able to fix the Q point at the center of the load line. If not, the motive is lost, and you may get a random amplifier operation. It may not be faithful amplification. It could be on state switching or off state switching. You do not know. That's the reason I said random operation, you may get it. Fine. Now, since there is lack of data over here, what we do is we go with kind of rule of thumbs, okay, or the design rules, we would say. Okay, the first design rule, you can write design rule. Okay, so in the first design rule, what we assume is that let VE is equal to 10% VCC. Okay, so this is your first assumption. Okay, and this assumption is based on what logic? This assumption is based on rule of thumb. Okay, rule of thumb in the sense there is no scientific theory which can support this particular assumption, but the practical results are supporting our assumption. Okay, theory cannot be derived, but from the practicals, we can say that whenever we assume this particular condition, we will get favorable results. So that's called as rule of thumb. No question asked, but you have to consider. Okay, that's the meaning of rule of thumb. Okay, now this particular rule ensures that the value of RE, okay, neither too large nor too small. Okay, so this particular design rule ensures that the value of RE neither too large nor too small. Okay, so basically you would get RE within an optimum value, which is desired, right? I mean, as much as possible, your amplifier should be able to give you a high output as much as possible. Okay, but at what cost? At the cost of stability. So that's the reason, RE shouldn't be too large or RE shouldn't be too less. So we should go for an optimum value of RE. So optimum value of RE. Okay, let me round off this. Can be obtained provided we follow this particular rule of thumb. Okay, hope you have understood. Fine. So let me rewrite it. Let VE is equal to 10% of VCC. Okay, so please don't change this percentage. Okay, this is design rule. So 10% of VCC. So VE is equal to 10% is 0.1 into VCC. VCC is given as 10 volts. So it is 1 volts. Okay, but what is VE? VE is equal to IE into RE. Approximately we can write IC into RE. So therefore, resistance RE can be found as VE divided by IC. Okay, so VE is 1 volt divided by IC is 2 milli. So that will give you 500 ohm resistance. Okay. Now, there is no standard 500 ohm resistance. That means to say, if you go to any electronic shop and if you ask for give me 500 ohm resistance, he may say, I don't have 500 ohm resistance. So what you have to do is you have to choose a nearest standard resistance. Choose nearest standard resistance value. Okay, so the nearest standard resistance value is 470 ohm. So let's choose RE as 470 ohm. So this is a standard resistance value. All right, so done. What we have found? We have found RA. Now we are left with 3 more resistances. Okay. Right. So this I will write it as first part of your design. Now let me take up the second part of your design. So Again, let me consider the output loop. So what I will do, apply KVL to output loop. Okay. So this particular step 2 is already been discussed in the previous problem, right? Apply KVL to output loop. So what do we get? VCC minus ICRC minus VCE minus IA into RE is equal to 0. So IA into RE is your VE, right? And VE is 1 volt. So you can write 10 minus 2 milli into RC minus 5 minus 1 is equal to 0. Or you can write RC is equal to 10 minus 5 minus 1 divided by 2 milli. Okay, how much you'll get? 4 volts divided by 2 milli is 2 kilo ohm. Again, you don't have 2 kilo ohm standard resistance, so you can write choose a standard resistance of 2.2 kilo. So 2.2 kilo is the nearest value. Okay, so let me write that's your RC. So the output resistances have been computed. Okay, RC is 2.2 kilo ohm. Done? Any doubts? Just let me know if you have any doubts. No doubts?
No, sir.
Okay. Perfect. All right then. Now let us go to find out R1 and R2. So R1 and R2 are found on the input side. So obviously you have to shift your attention to the input part of the circuit. Okay. So to find R1 and R2, what I will do is I will consider the equivalent circuit, which has been already discussed. Equivalent circuit of input side. Okay. So what I will do, I will recreate the input circuit scenario. Okay. So this is your R1 and this is your R2. All right. And this is your base and this is your ground. And base to ground, let's define it as VB. This is VCC. So VB, we can write it as, okay, VB is what? Main voltage into resistance of, the resistance across which VB is measured divided by sum of resistances. Okay, but what is VB? Okay, I think in the previous problem also I had written VB. Okay, VB is this. Okay, if at all you did not get it, what exactly is VB? So this is your emitter resistance RA. Okay, and this is your ground terminal. Okay, this is your base terminal. So I am defining VB as base to ground voltage. This is your G node or the ground. Okay, so this is my VB. Now base to ground voltage is nothing but base to emitter voltage VB plus emitter to ground voltage VE. Okay, this is what I was referring to. This is minus, this is plus, because ground is always at lower potential. And between base and emitter, your base will be at higher potential and your emitter will be at lower potential. So from this particular circuit, you can write VB as base to emitter plus emitter to ground, which is VE. Okay, base to emitter is 0.7 volts and emitter to ground VE. Okay, we have assumed VE as 10% of VCC. And how much did we get? VE value as 1 volt we got. So your base to ground voltage is 1.7 volts. 1.7 volts. Okay, so that's VB. So you can substitute the value of VB, and VCC is also known. So VB is 1.7 volt, VCC is 10 volts. But what is R2 and what is R1? We don't know. Okay, we don't know what is R1 and what is R2. hence we have to go for, recreating the input circuit scenario. So what I will do, let me redraw the input part of the circuit. Okay. So this is R1, this is R2, this is your base terminal, which later on gets connected to the base terminal of the transistor. This is RE, this is ground. Okay. All right. So this is your collector terminal. This is RC. This is plus VCC. Okay. Now let me mark the base current. This is your base current IB. Okay. Observe carefully. This is your base current IB, emitter current. Okay. Collector current. So IB plus IC will flow out as IA. Okay. Now, through R1, let's consider current I1. And through R2, let us consider a current I2. Okay. So, at node B, you can apply KCL. Apply KCL. Okay. So at node B, when you apply KCL, what do you get? Incoming current is I1 and outgoing currents are I2 and IB. So I1 is equal to I2 plus IB. Okay. Now, your I1 and I2 are the currents which are directly derived from the power supply voltage VCC. So the magnitude of I1 and I2 is very, very high compared to IB, because I1 and I2, as I said previously, it is drawn from the power supply voltage, and power supply voltage is kept at 10 volts, which is significantly high. Okay, so let us choose current I1 is equal to 10 times IB. Okay, let us choose current I1 is equal to 10 times IB. Why? Because I1 is very large compared to IB. Okay. Now I have chosen 10 times IB. Okay. You may choose 100 times IB, 50 times IB, so on and so forth. Okay, you can choose. But when I choose I1 is equal to 10 times IB, I will get standard resistance value. Okay. Standard resistance value. If you choose greater than 10 times IB, things will work out, doesn't matter. But the problem is you may not get standard resistance values. Once again, even if you don't get standard resistance values, then you will have to go for a kind of tailor-made resistance values, wherein you may have to go for several series and parallel connections to get the desired value of resistance. Okay, that is okay, fine. But you can always follow this particular rule that current I1 is 10 times IB. Okay, so current I1 is 10 times IB. Therefore, I2 is equal to, what is it basically? 10 minus IB, right? So I2 is I1 minus IB, or 10 times IB minus IB is 9 IB. 9 IB. Okay, so let me write I1 is equal to 10 IB and I2 is equal to 9 IB. That's all we need to calculate the resistance values. All right, fine. So resistance, okay, let me write. This is VB, right? This is VB, base to ground voltage. Base to ground voltage is VB. And how much did we get VB as? 1.7 volt. Okay, so VB is equal to current into resistance. So what resistance? R2 resistance. And what current? I2 current. That implies resistance R2 as VB divided by I2, or VB 1.7 divided by I2. What is I2? I2 is 9 times IB. Okay, where IB is equal to IC by beta. IC is 2 milliamperes and beta is 100. So 2 milli divided by 100. Okay, so that is about 20 microamperes. 20 microamperes. So it is 1.7 divided by 9 into 20 micro. Okay, so can anyone tell me what's the value of R2? $8.5 kilo ohm. Can anyone confirm? Did you get? R2 has 8.5 kilo ohm?
Yes, sir.
Good. So again, you don't have exact 8.5 kilo ohm resistance, hence you can go for choose R2 is equal to 10 kilo. Okay, so round it off. R2 equal to 10 kilo ohm. This is your standard value. Okay. If you want exact 8.5K, then probably you may have to use several resistors in combination to get the precise value of 8.5K. Okay. All right. Then finally, we are left with R1. R1 can be found either using, okay, so R1 can be found. R1 can be found by using VCC is equal to, sorry, VB is equal to VCC R2 divided by R1 plus R2. Okay, because we know R2. R2 is 10 kilo ohm. I'll write it down. And VCC is 10 volts and VB is 1.7 volts. Or you can also find R1. Okay, so what is R1? Sorry, okay, not R1. Voltage drop across R1. Okay, what's the voltage drop across R1? What is the voltage drop across R1? It is basically I1 into R1, right? Voltage drop across R1 is I1 into R1, okay? Or resistance R1 is equal to voltage across R1 divided by current. Okay. Now, voltage across R1, if you see closely, since you know nodal analysis, that's the reason I'm telling you. So voltage across R1. So resistance R1 you look at. On one side, this R1 is connected to VCC, and on the other side, this R1 is under the influence of base to ground potential VB. So voltage across R1 can simply written as VCC minus VB divided by current I1. All right. So this is also you can use. You should get, you know, same answers. So VCC is 10 minus VB is 1.7 divided by I1 is 10 times IB, right? So 10 minus 1.7 divided by 10 into 20 micro. That's 200 micro. So how much you are getting? 41.5 kilo ohm you are supposed to get. So R1 you'll get 41.5 kilo ohm. So there's no standard resistance value. Hence we choose R1 is equal to 47 kilo ohm. Okay. Or you can also go for 39 kilo ohm. Okay. Since in lab we don't have 39 kilo ohm resistance, hence we go for 47 kilo ohm. Okay. But the standard resistance value, there's a standard resistance value of 39 kilo ohm also. Okay, so that completes your design problem. Okay, yeah, it's 9:30. So therefore, R1 is equal to 47 kilo ohm, R2 is equal to 10 kilo ohm, RC is equal to 2.2 kilo ohm, and RE is equal to 470 ohm. Okay, that's how we design voltage divider bias circuit for a limited set of specifications. Okay, all right. So I'll stop my class here. Okay. So in the next class,
Excuse me, sir.
yeah, tell me.
Sir, R2 is coming as 9.4 kilo ohms.
Which one? 9.4.
R2
R10. Okay. Fine.
is
Let me-
9.4.
Yeah. 9.4, no?
Yes, sir.
Okay, let me write then 9.4. Okay. You have checked, right? Fine. 9.4.